Just some notation from last time for people, because I think I didn't say this precisely. So lambda is going to be the Novikov field. I already introduced this. And inside of this, we have lambda star, which are the non-zero elements, invertible elements. And inside of this, we also have lambda 0, which are the elements of valuation greater than or equal to 0. Okay, which again, I just want to say this is like norm less than or equal to 1. And the point is that if you look like at the complex numbers of norm less than or equal to 1, and you try to add 2 of them, then the norm may be bigger than 1. But with the Novikov ring, it doesn't work. It doesn't work that way. So if this is actually kind of this is a subgroup, a subring actually. Okay, and then inside both of these, we have the unitary element, which I'll call u lambda. And these are the elements of valuation equals 0. In other words, the invertible elements means just valuation is not equal to infinity. So this is when we do algebra, that's how we want to think about it. And when you do geometry, you instead want to think of this lambda. The point of lambda is something like some kind of A1. And the point of lambda 0 is some kind of unit disk. And the point of u lambda is some kind of annulus of valuation, where the 2 radii of the annulus are equal. And the point of lambda star is an annulus where the biradii are infinity and plus infinity, but I won't really use this. So that's the picture you should have in mind. And one thing I alluded to last time, and I didn't quite say it precisely, is that if we have, given, and I still won't say something that precise, but given L inside M, and let's actually make it an immersed Lagrangian with transverse double points. Okay. So let's assume that n, which moreover bounds no holomorphic disk for some j.
The diagram of this confusing.
Yes. I mean, yes. That would require for the maps to be non-trivial. I mean, the maps are all just inclusions. But yes. And bounds no holomorphic disks for some j, then we should really think of the usual Floer cohomology. Floer cohomology of L can be written as in terms of, can be expressed in terms of the fiber product over M of L. It's basically the cohomology of this space with some degree shift. So let me say a little bit more. So note that inside of this we have L, kind of included as the diagonal, and we also have the double points.
Do you really want to consider immersed ones rather than embedded ones?
Yes. Just because somehow it will give us more examples to play with. So then we have the double points. But now to each double point, so I want to say oriented.
So what means no holomorphic disks?
It means that there's some specific j, so that there's, yes, thank you, Paulo. So that it bounds no holomorphic disks or one-gons. So what that means is that there's some specific j such that you don't see any holomorphic disks with boundary on L, nor do you see any things of this form where this is a double point. Pardon? Teardrops. Holomorphic teardrops, of course. Okay? So inside, so there's L, and then there's the double point. And the only thing that I want to point out is that for the double points, we have, because I assumed that my L up here, I kind of backtracked and recalled that it should be oriented, that we have some kind of assignment of a plus and a minus to the double points. So assign, I'm going to say kind of an integer, not an integer, an element of Z mod 2. Oh, sorry. assign 0 to positive intersection and 1 to negative. Okay, actually, really this should be corrected by a sign having to do with the dimension, but I'm just going to be sloppy. Okay. Yes?
So they should each appears twice. Each intersection points appears twice. Once with 0, once with 1, right?
No. No. So if n is odd, everything appears twice. And if n is even, then you don't know. Then they may all be even or they may all be odd. Okay?
Okay, so the fancy notation L cross ML just means you have a copy of L,
Yes.
and then you have ordered double points.
Yes. Ordered double points. Yes. And all I'm saying here is that
Why do I sign 0 and 1 instead of +1 and -1?
because I want to write now to say the following thing, that this Floer cohomology is isomorphic to the cohomology of L, direct sum. Well, I could have cheated and put in 0 for this one too. Direct sum, the cohomology of the double points shifted by this by 0 or 1 depending on the plus or the minus, but then there is a anyway, let me just put this delta. Sign delta, and this formula is actually not correct because you have to put in the parity of the dimension, but anyway, I don't. Whether the intersection should actually contribute, whether the positive should contribute even to Floer cohomology or odd to Floer cohomology actually has an n in it.
So in other words, this is just a Z mod 2 graded equality anyway, because you're only
Yes,
assigning
everything is
0.
Z mod 2 graded.
Okay.
I'm confused. It seems to be bigger than even just, the rank than all the double points. But
No. This is
Yes, every double point occurs twice.
so that's exactly. So it's in the fiber product, not in the symmetric whatever. The fiber product over M. So this is a pair of ordered points in L whose images in M agree, but ordered.
I'm still confused. I mean, if you write on the Floer complex,
That's the Floer complex.
it's generated by the double points, right?
No, there's also L.
Right, because it's like an extension of singular cohomology. It has to be.
But it's okay. I think that let me give you an answer that maybe make you happier, just for a second. If you took L and you perturbed it,
Yeah.
okay, then you would see as many intersections. So you would see some collection of generators that just come from like one sheet with itself, and that would generate this piece.
But why didn't you draw a figure 8?
L is the union of two embedded Lagrange units.
So for a figure 8, okay, no, for a figure 8, this answer that I provided here is basically the cohomology of S1, direct sum rank 2 piece. Yeah, rank 2 vector space. And you could recover the same thing by thinking about this.
I thought you meant intersection points.
Okay, where somehow, anyway, maybe now I'm not going to do too much. These are the 2 points that came from here, and then there is the stuff that comes from the cohomology of S1, which is somewhere out there. Maybe use a different color, here and here. Okay, so anyway, but now what I explained last time, so this is the thing. And now but you could ask yourself kind of what are the objects of the Fukaya, these Z2 graded Fukaya category of M that should be supported on L and are simple. Okay? And what I explained last time is that what we should do is we should take inside, so I'm going to put in quotes because we don't have a formal definition yet, the moduli space of simple objects of simple objects of the Fukaya category of M, and this is Z2 graded with support on L. Well, it's as follows: is you take H1 of L with coefficients in this unitary elements, and you take the product of this with H odd, okay, of degree greater than 1 of L with coefficients in lambda 0, and you take the product of this with the second part here, H odd, but now you don't impose the condition that is greater than 1 of, and then just apologize for the whole world notation, double points coefficients in lambda 0, and then you put in this shift. Which means what? Which means if you have a double point that contributes to odd degree, such that the degree here is odd, then you get a copy of lambda 0 for that. Okay? And geometrically, the one who thinks geometrically, that this gives you something like this disk. Remember, I tried to think like you should think of lambda 0 as giving you some kind of unit disk to the first Betti number of L cross, annulus to the first Betti number of L. This annulus of radius by radius 0, 0 to the first Betti number of L cross the disk to the sum of the Betti numbers minus B1. B is the sum of the odd, B odd minus B odd. B odd is the sum of B2k plus 1 minus B1 cross D, and here I'm just going to write to the number of odd double points. But can taken with order. Taken with order. Okay, great. And so the point is that like every single one of these domains is something that I talked about last time. Yes. Sorry.
I was going to ask. So when we talked about why we get all of D.
Yes.
There's a moment of justification
You mean
coming from Gromov compactness. When you cut it by an odd-dimensional cycle.
Yeah.
The count's still finite and so on.
Yeah.
And of course that doesn't happen for a local system on
Yeah.
the left, which is why you get this annulus. So
Sure.
why does it happen for a double point?
I allude. So these two, strictly speaking, this is just Gromov compactness.
Yes.
This one, the reason that you get this entire disk is by a result that says that basically it takes a definite amount of energy to pass through a double point. So this is the reference I gave is Fukaya 2009 Berkeley lectures. So I'm sorry. But if you want a specific instance of this, proved probably in less generality of this, there is that paper of Zillibach, Ekholm, and Latchev. Okay? And it proves something of relevance to this result.
Excellent. Would anybody else like to slow down, Mohammed?
I'm sorry. I didn't have coffee this morning.
Gosh, I can only imagine what
I can. Yeah.
I would like to slow down.
Yes. Sorry. Yes.
So, for ordinary cohomology, it's clear that these objects actually exist, which means it's unobstructed.
Yes. This was.
But how about for the double points?
You're right. So thank you. I should have imposed a much stronger condition here. I should have actually said no holomorphic polygons whatsoever. And I will come back to that, and I will say something like that in a second. Okay, just exclude all of them. And then we will talk about what happens when we have polygons.
So you're saying you need to exclude all of them for this to be part of this moduli space.
Yeah, so let me just, yeah. Okay.
When you speak of direct sum, what do you mean? Is it really the canonical product, or is it shorthand for having some extension which you don't know?
No, in these assumptions will give you that it's just a direct sum. There's no extension whatsoever taking place here. Yeah. Okay. So now, what I want to do, the kind of slogan, is that we should think of this. So we need a name for this space. So let us call this space Y of L. So that Y of L is a rigid analytic space.
So when you stated the cohomology, there were a slightly stronger assumption, probably of no holomorphic polygons or something. Yes.
Yes, it was already stronger assumption of no holomorphic bigons. Just to compute that cohomology is what it is. Thanks. So otherwise you have a differential. Okay, so YL is a rigid analytic space. Okay, and somehow this rigid analytic space, it only depends on L itself. It doesn't depend on the embedding because we put so many conditions. Okay, and in general, so if we drop the conditions on no holomorphic disk, 1 second. Yes?
It does not depend on the immersion? No.
Well, okay, it just depends on the topology of the immersion.
Right, topology.
Right. Doesn't, yeah. Yeah. So, literally, maybe I can say something. The way I think about this Floer cohomology is that if I were to take the immersion and take some kind of tubular neighborhood of the immersion, that's the Floer cohomology I would get. So it doesn't depend on the rest of the space in any way because, well, I assume that there's no disks. So there doesn't see it. Okay, so the conditions on the holomorphic disks, we should get, first of all, we get some kind of equation on this space. This space imposing the condition that a certain curvature, let's say M0, is 0. And just because of the examples which are easiest to present, I want to say kind of mod H 0 of L. Okay, this is called being weakly unobstructed. And then 2, maybe I should put equations, because, yeah. 2, we get some kind of equations imposing the condition that the differential that the homology of the induced differential in Floer homology
Wait, the induced differential on ordinary cohomology.
well on
Not this cohomology.
Well, let's finish the sentence.
anyway the homology of the induced differential is non-zero. Now this, by the way, is equivalent to two things. First, it's equivalent to the identity in H0 of L not being in the image of the differential. Sorry.
I think we should be maybe a little cleaner, right?
Yeah.
So this space YL carries a trivial vector bundle. This fiber is the even dimensional part.
Sure.
And the equation means a section of this, or a map into the even one.
Yes.
And that cuts out.
That cuts out this
set.
zero set. Yes.
And then that zero set carries a bundle of Floer cohomology groups.
Yes.
And
Well.
for some
Yes.
reason you had a sheaf of Floer cohomology groups.
That's
For
right.
some reason you want to take the open subset of the zero set where that is not missing.
Because that's where Floer homology is interesting. I mean, otherwise you get zero objects in the Fukui category. So let me do an example. I think maybe it's best to do this. So this is let's take this as a slogan, because I didn't say this was a slogan. That's what we want to do, and then we'll do yes.
So just to go back to the order above, and so to restrict to something special, so you say they are simple objects, right?
Yeah, that's somehow just intuition. I mean, this was not a definition. Okay, but if you want non-simple objects, you would want to put in higher rank vector bundles on L. Right. This is like one copy of L.
Okay.
Yes.
So, if we're talking about like moduli space as like isomorphism classes of objects.
Yes. Then you would take this zero locus and you mod out by some group action, and then we would be talking about some kind of. Then yeah.
Okay, but my question is about when you wrote sort of cohomology instead
Yes.
of cochains, or like the space of cocycles.
Yes.
When odd is greater than or equal to 3.
Yes. That's okay.
So if we want to think of it, it really is this. It's not.
You can transfer from cochains to cohomology. And think of everything as living at the cohomology level.
So the question was, shouldn't I be, when you solve this equation under 1, you're usually solving it in cochains, and then there is a very large symmetry group.
My question applies just even with the no disks condition.
Yeah.
Yes,
Yeah,
but
yeah.
So the answer is that this very large symmetry group there is a natural finite dimensional slice which makes it simpler, and you land in here. That does not kill all the symmetry, but it kills a lot.
Yeah, there's no symmetry. No. Anyway, yeah. So I think of the homologically, you think of this as transferring from cochains to cohomology. So you know that you can solve the equation at the cohomological level instead of solving it at the chain level. Yes?
So for the first bullet, so that says that if we drop the condition on disks, then we get equations that impose that m0 is 0.
Well, we get an equation, which, so Paul said it best, which is that you get, you take the trivial bundle over the space, which is given by the even dimensional cohomology, and you get a section.
Plus the stuff there. H even double points.
Yes, I'm sorry. The even dimensional Floer cohomology. And then you get an you get a section of that. Okay, maybe I should describe what this section a little bit. So this section is so this m0. Naively, you want to think of m0 as just counting disks with one mark point plus these teardrops. Okay, this is the part into the cohomology, and this is the part into the cohomology of the double point. Okay, but then if you feed in any element of this space, then you can instead count so for B in this space, you're counting this sum over all such expressions, seeing whether you get something 0 or not. And if it's 0, then you're in the I don't know what to say, like Moore-Cartan. I don't want to call it scheme because people Moore-Cartan scheme. Let's say that. And then somehow, if we have points where Floer homology is unobstructed, but Floer homology is trivial, then that's not so interesting. We really want this space of non-zero objects, usually. So let's do an example. And this is the example that's Cho, and then Cho and O, and then Fukaya O to Ono. So this is just toric varieties. And so L is going to be embedded, and L is going to be just this Lagrangian fiber of the moment map. And I'm not going to do a general case. I'm just going to do CP2. And the moment map is like this. And so you can parameterize the fibers by the points down here. And in fact, the other thing you could do is you could parameterize LAB with A greater than or equal to 0, B greater than or equal to 0. And these, I want them to be the area of a disk passing through Maslov 2 disk, I should say. But anyway, a disk with boundary on L, disk with boundary on L and B, and that intersects the line x equals 0, y equals 0 once. So
also knows as the x and y coordinates on the picture there.
Thank you. Yes. This is going to AV intersecting lines once. Okay, but as Paul is saying, so you should think of them as somehow, tropically, you should think of them as this line and this line. Okay? And now, for each such torus, we get an equation. For m0 of this torus. And this equation, you should think of it as a function on h1. I only want to take, this is all there is, h1 of L with coefficient in u lambda. And what is this function? It depends on A and B, and it is given by t to the A times x plus t to the b times y plus t to the 1 minus a minus b over xy. And if you're wondering what this last term is, that's because I didn't talk about the z equals 0 axis, and there's kind of complete symmetry. So there's also kind of a disk that goes like that. Okay? So this is this equation. If you actually, the point is, if you take this, you should interpret this equation as being as giving you an element of h0 of L, AB. And I told you that the equation we should be imposing is that something is 0 mod h0. Okay, so in our case, of course, this equation is interesting, but somehow we should consider all of these objects as potential objects of the Fukaya category. We don't have any trouble doing Floer theory for them. But now comes the next equation, which is the one that imposes the condition that the homology of the induced differential is non-zero. And we're not going to derive it, but what you get.
So can you tell me that the exponents of the t's guarantee that it's an h0? So it's,
No, it means that you have to think about what is this counting. And this is counting some kind of weighted disks which pass through a generic point. Okay, and because they're passing through a generic, we're just counting how many there are without imposing any other constraints. You really get that this is like the coefficient of m0 times the unit of L.
so a is the area of such a disk.
No, A is, okay, so A,
Yes.
yeah,
A is the
area of this disk here. And B is the area of this disk, and 1 minus A minus B is the area of this disk. Okay?
In other words, if you count m0, you only get some multiple of the unit class, and it's this multiple.
Yeah.
So there's no other knowledge class.
So our parameter space is given by these x's and y's. That's what lives in this h1 of L, which, by the way, is just a copy of u lambda squared. Okay? So we get non-zero HF if and only if x and y is a critical point of this function. Okay? And now it's, now you just do some computation. So this is, you do some computations and you see that if you want a critical point to lie in u lambda.
No, we should do that computation. So t to the, we differentiate this function x.
Sorry, you want? Sorry, I should say critical point in what variable? So this is a critical point in the variables x and y with a and b fixed. Okay, that's the computation that we are doing. Okay, so you take the derivative with respect to x, you get t to the a plus minus t to the 1 minus a minus b over x squared. This is the x derivative. And then you take the y derivative, t to the b minus. Something very easy is going to happen in a second, but it's just times y. Thank you. Xy squared. OK, and now you would like to be able to plug in x's and y's of trivial valuation so that both of these functions vanish. OK, so we need a solution with, I'll repeat it again, valuation of x equals 0, valuation of y equals 0. And I'm told if you read rigid analytic papers where they do computations every once in a while, they say arguing with valuations, which means noticing that in order for this to vanish, then the valuation of this needs to be equal to the valuation of this. But this has 0 valuation, so that means that this number must be equal to this number. So you get a equals 1 minus a minus b, and b equals 1 minus a minus b, okay? Which hopefully implies that a and b are both equal to 2/3, 1/3. I didn't say that this is CP2 with area 1.
And you don't have to argue by valuations. You can just solve for x and y.
You can solve for x and y and notice that the solutions lie outside the set. Yes.
So there are 3 points and the evaluations.
Well, we haven't quite gotten to, yes, you're right. Paul is saying you could also go and find that there's 3 points. OK, but so now something which I'm...
You're still saying that you get non-trivial flow homology exactly if this is true.
Yes.
The reason about that is derivatives that appears as differentials in the flow.
Yeah, so once you take these derivatives, you can interpret them as the differential from h1 to h0. So indeed, so Paul said, well, you could say that you could imagine you have a vector bundle, and then you have a section of this vector bundle, let's say m0, and then moreover you have some differential, but somehow the two things are not independent data. So, okay. So now something important happens, which
How
Yeah.
does it imply Floer homology non-zero?
I didn't explain it. I basically said this equation, this term, okay, is the coefficient of 1 in the differential of the class of one class in H1. So you have some differential that goes from H1 of L to H0 of L. Okay? And what I'm saying, by taking this derivative, you're basically saying take what the generator here that corresponds to x, and this term happens to be the coefficient of 1 in that. I'm not going to derive it.
And if it vanishes on H1, so if you plot the differential, then it vanishes everywhere.
Well, yeah, because, yeah, so yeah. Well, in this case, there isn't enough room for it. Yeah. Yeah. So, okay, so that was, so now something important happens, which, you know, if I were giving kind of 4 lectures, we would spend much more time on. But I want to notice that this equation is essentially the same for all A and B, it's just except that those coefficients are changing. Okay, so this is kind of, I would say that this is a key observation.
No.
Let me. This was one Lagrangian at a time. I said take this one Lagrangian LAB, which bounds this disk and this disk of area A and area B. Then you get this function with an A and a B in it. Okay, but.
Will you later claim that this thing can be done in families, and then you get?
Yeah, so it's a key observation. So we can identify the potential, or the potential is that function. So let me just write W. W for LAB. Okay, we're now here W. Let's think of it as a map from the biannulus A squared to lambda. Okay, as the restriction of the potential W again for L. And just for convenience, it's best to center it at our favorite point, which is 1/3, 1/3. Okay, to the annulus inside lambda star squared with biradii, so given by valuation of the first coordinates equals 1/3. A minus 1/3 maybe, and valuation of the second coordinate given by B minus 1/3. Okay, so what does that mean? Originally, I said that we should take this potential and think of it as being defined on first cohomology with coefficients in U lambda. Okay, so originally I said, so W was defined on this annulus, basically annulus of radius 0 squared. Okay, but it so happens that the formula that we get is just a polynomial, and so it actually extends naturally to lambda star squared. Okay, and we could ask, what does it mean? What does this extension mean? And the answer is that the extension actually allows you to recover the potential for the other Lagrangian tori. So we can recover the extension for the other tori by kind of, well, I'm sorry, the function for the other tori, potential for the other tori.
Question?
Yes?
Why does valuation x equals a minus current valuation y equals b minus current give you an annulus?
Well, valuation A equals 0 gives you an annulus. By definition, I mean, now how we define the annulus.
She's right, you're wrong. Because A and B are also restricted by A plus B less equals to 1.
Yeah, okay, well, then we're going to get out to some. You mean, no, if A and B satisfy, I don't quite know what you mean. If A and B both satisfy that equation and this, then they give you an annulus. I don't quite know what.
I mean, what is the thickness of the, that's an
0,
annulus.
0,
Zero thickness annulus, that's right.
0.
It
But,
just shifts.
Yeah,
okay.
Okay.
okay, so by restricting, so again, so you can recover. I can say, I think I'm going to say something in a minute. Just give me, just, they're both a zero radii. Okay, I think I know what you're saying. I think I know why you're confused. You're confused because I didn't write to the product of annuli in this space, which the product is given by, the first annulus is given by this condition, and the second annulus is given by this condition. They both have thickness 0. So it's just a point. Sorry, what? So it's just a torus. Yes, sure. But I think of it as an annulus of radius 0. So can recover the potential for the other tori from this one function. Yeah. 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 From the single function. Okay? So I just want to say a little bit more. So the picture is like this. So this is lambda star squared. And we have a map from lambda star squared to R2 given by the valuation. Okay? And when you go through this discussion, we've set everything up so that the origin here, okay, this is the fiber over the origin. Sorry. So let me just say it like this. The origin corresponds to the point L 1/3, 1/3. Okay? And now I'm saying on this lambda star squared, you get a function W to lambda. And then you look at the critical points of this function. And it so happens that the critical points of this functions all lie over here. But let's just imagine for a second that you had some critical point and the projection of this critical point lies somewhere here. Okay? Then what you would say is that this point here, even though I computed the potential only for this 1/3, 1/3, this point here would possibly give me some torus LAB. Okay? And that torus LAB would be equipped with a unitary local system with non-zero Floer homology. Okay? This is fine, except for the fact that Paul noted that we also need to impose that A greater than or equal to 0, B greater than or equal to 0, and A plus B less than or equal to 1. And if you draw it in this picture, it becomes what you'd expect it to be, something like that. Okay, just moved off a little bit. It's the same picture, just translation. And what that tells you is that critical points away from this critical points away from this triangle are not, well, I want to say they're not physical. They have no interpretation as a Lagrangian torus equipped with a local system. And okay, so the magical thing is that for phonotoric varieties, it turns out that all the critical points lie here. Yes?
Yeah, can I just check, what Helga was talking about, varying the torus? Yeah. When you say it's defined on A2, you're now saying this function depends nicely on A and B.
I mean, that's what I mean when I say define the lambda star squared.
Sorry, is that like this?
Yes, that's exactly what I mean.
Okay, so now you're making a new.
Yeah.
Previously, we've been thinking about just like
one at a time.
one individually.
Right. It actually is the same function on lambda star squared, restricted to different annuli, products of annuli of radius 0. Okay, except that they're all embedded, as the fibers over different points of the valuation map. The one we prefer is the origin, and the other ones are other points.
Is there a bigger sense than continuity?
I mean, yes, it is an analytic function on this space. Okay, so that's what I wanted to say next. No, I'm not done yet. So in this case, this generalizes. So for phonotoric varieties, if you don't know what this means, just don't ignore it. For phonotoric varieties, this procedure always gives you a Laurent polynomial. Always get a Laurent polynomial. Okay, and now one summary of what Fukaya Ota Ono did in their series of papers on toric manifolds is that for any toric variety, this function W is an analytic function. And now comes some delicate points. So on the domain inside lambda star to the n, inside lambda star to the n, given by the condition that the valuation of any given point, let me now going to write z, lies inside, and this is where the delicate point is, it lies inside the interior of the polytope. This is the moment polytope. So I won't, you know, it would take too much time. I mean, roughly speaking, in this theory, as I'm doing it, closed regions in R2, in Rn, are like the basic building blocks. And so this open thing is not a basic building block, so you have to exhaust it by closed things, and that makes everything a little bit more delicate. But that's what they proved. Okay, yes?
In quoting this FOO result,
yes.
You're sort of restricting to the H1 part of the bounding chain?
Restricting to the H1 part of the bounding chains, and have to think whether you could. I mean, the point is that the higher cohomologies, they are not entirely encoded by this W. There's some additional information that's there, and I'm not recovering it. I'm only talking about the H1 part. Is that okay?
In some sense, the functions on the tangent space of the minor space, right? How do you identify the minor space?
So right now, I'm just doing something naive, and I'm just saying the moduli space. I identify. I don't quite know what to say. So I explained here how you can identify certain points in lambda star to the n with certain Lagrangian with certain copies of with basically Lagrangians with given areas together with choices of classes in H1. That's what was happening here. And I'm saying on that space you get some function, and that function is analytic. And the critical points are the Lagrangians with non-zero Floer homology, and then there's much analysis of how this knows just about everything that there is to know about quantum homology and things like that.
Okay. So in examples of non-final,
yes?
right, is that the natural
boundary for? Yeah, I mean, I don't. Let's say. I haven't done a computation to be able to tell you the answer. Yeah, there are very few examples where it's somehow computed.
W not a polynomial anymore?
No, certainly W is not a polynomial. That is clear. That we know. I didn't check the radius of convergence of these W's.
I mean, sometimes you pick out special Lagrangian, yeah, but you never talk about it, right? I mean, you have a function on some space.
Yes.
And when you say the points in the space correspond to Lagrangian submanifolds, but they're very special ones.
Yeah, they're the ones that we started analyzing at the beginning. We're only talking about the fibers.
Do you have a notion of picking them out in the general context other than for correctness?
No, so what you should think about it is if you take one Lagrangian, you want to think about all the ones that can get to it by deforming. And you get some equation on that space. That would be one reasonable way of trying to do it. Yes?
Can I continue next question?
Yes.
So when you're saying that you can recover this
oh, sorry. Yes?
recover this thing on this star squared, you mean that like you do sort of change the variables by taking sort of you said the valuation x equals to something.
Yeah.
So you're saying like you can change x for sort of.
So in this case, it's very easy.
Fixed guy which has valuation.
Yeah, you do change the coordinates. X goes to t to the 1 minus to kind of a minus 1/3 x.
Right.
That will switch you from the fiber at 1/3 to the fiber at a. And then that's how these functions are related. Okay, so I don't have very much time. I have half an hour left. But I wanted to do an example where you get a much more interesting. So in this case, it turns out all these functions have isolated critical points. And so the kind of loci you get are just points, maybe with multiplicity. And so maybe what I'll do is I will not mention the other example where you get kind of a more interesting function, because that will take us too far. Instead, I will try to say something about where does the analytic structure come from. So far, again, all we have is you take these Lagrangians, you observe that it so happens that some function behaves well, but we don't have kind of a Floer theoretic explanation, Floer theoretic origin of the kinds of functions that arise let me just say affinoid rings. Okay, and of course what's going to happen is that we're going to have some definition, something that just kind of Floer theoretic, and in some cases it will give us an affinoid ring, and in some other cases maybe it'll give us something more complicated. And so to do this, I want to go back to, again, this philosophy where we should just first analyze what happens when there's no holomorphic disks. So now I want to assume that L is embedded. No disks. By the way, the other example I was going to do involved immersed Lagrangians. So maybe if I'd known that, what? Well, not now. Anyway, maybe I'll come back to it at the end. So assume L is embedded, and yeah. So I want to understand kind of where does this. So then when I make the statement, kind of this y of L in that case is just h1 of L with coefficient h1 of L, just h1 of L with coefficient in u lambda. Just recall this cross h odd greater than 1 L with coefficient in lambda 0. Okay. So what does this mean? Where does this come from? Or what does the kind of, if we want to think of this as kind of some space of bounding cochains, how should we interpret the analytic structure on this space? And so the answer is that we should think about the based loop space of L. So the based loop space of L at some base point, which I'm not going to specify, is an algebra. So the homology of the base loop space of L is, again, is a graded algebra. Okay. And now we want to do the following thing. I just want to say, I want to consider this homology with lambda coefficients, and I want to consider the completion with respect to the t-adic topology. Completion with respect to the t-adic topology. So what does that mean? What that means is that you're allowed to write an expression of the form t to the lambda I alpha I, okay, as long, this makes sense, as long as limit of lambda I goes to plus infinity. No, nothing here. Later. I mean, later. Somewhat. Here they don't appear. As a group. Yeah, group. Thank you. Suspension spectrum is an algebra. So yeah. So that's all we do. Nothing sophisticated. In fact, this thing, which is not sophisticated, makes it very easy to see that, if you're worried about issues of like chains versus cohomology, there's no issue whatsoever. This cohomology, this completion of the cohomology is just the cohomology of the completion of the chains, because the differential doesn't know about lambda at all. It doesn't interfere with anything. Okay. And now there is a general fact. This general fact is most well known in the Z-graded case. And it says basically that h1 of L, and I'm just going to put a coefficient in lambda, this is the same as the moduli space is the space, I'm just going to say space of rank 1 modules over this algebra homology of the base loop space. Okay? So now, Z-graded rank 1 modules. Well, I wrote Z-graded there, so that's kind of explicit. So now we have inside of this something, which is h1 of L with coefficient with this lambda 0, which is this disk inside this, product of disk inside this copy of AN. And well, somehow this should, so the space of modules should become smaller, so the ring should become bigger. So this embeds, this is the space of modules over the completion. Okay. So the toy case, there's two cases that I want to talk about because they are the, sorry, this was supposed to be lambda star. and this is supposed to be u lambda. Okay, so why? So let's do the case of L equals a torus. Yes. So the reason is that if it's a z-graded module, then in fact only h0 of omega L lambda matters in this description. Okay. Kind of, the algebra is filtered. There's h0, h1, blah blah blah. But there's never any higher degree element that can multiply back to this. So you can just anyway. So everything is determined by what happens here. And now, if you are if you have a module over this, this is just a representation of pi 1 of L. Okay. And if it's over lambda, pi 1 of L valued in lambda, and then the h1 of L stars is just the monodromy. Okay. And now maybe you could ask, what about this versus this? Okay. And that I'll say something. So, but I'll do it in an example. So L is a torus. So then h of omega L with coefficients in lambda, this is the same as h0, which is the same as the Laurent polynomials in some variables z1, zn. Okay. Actually, you can, this was some kind of choice of coordinates. You could just say that really this is the group algebra of the group, which is h1 of L with coefficients in z. That's literally what it is. Okay, and then last time, when I introduced this infinitely thin annulus, I said, what are the functions on the infinitely thin annulus? So, this is, you should think of this kind of algebraic functions on lambda star to the n. But the functions on A00, where Laurent polynomials, Laurent series, sum of ci z to the I, I'm doing just the one variable case, such that the limit as I goes to plus or minus infinity of the valuation of ci equals plus infinity. Okay. But this is just the completion of this thing here with respect to the, if I just think of it as a lambda vector space and I complete it with respect to the t-adic topology, that's what I get. This is completion of Laurent polynomials. Okay, so that tells us that if you apply this basic computation here to tell you that, in fact, this completion of the homology of the base loop space of Tn with coefficients in lambda is the same as the ring of functions. Well, maybe I didn't quite use this notation, but I think it's clear what it means. So I use this notation when I didn't have powers, when I didn't have plus or minus, when I did it for usual polynomials. But you can do the same thing for Laurent polynomials, which is the ring of functions on this annulus of radius 0, 0, z1 cross zn, which corresponds exactly to what I was saying over there. You can identify this with h upper 1 of L with coefficients in the unitary elements. Okay, this is the first example. So the next thing to do is to try to think about the case which is not z-graded. Because the case which is z-graded, you're not going to get very much. You're always going to get these annuli, and if you want something a little bit bigger than these annuli, maybe some disks, then you need some other some other kind of input. So there is a similar story with these Z graded case. There is a similar story in the Z2 graded case. It requires a little bit of care. If you want to assume that you have some kind of filtration, you start with something graded and then you add additional terms to this, to your module structure to make things not graded anymore. So, but anyway, I want to say kind of there is a similar story in the Z2 graded case, where H1 with coefficients in U lambda, in lambda star cross H odd bigger than 1 of L with coefficients in lambda is a moduli space, is a space of rank 1 modules over this homology of the base loop space. And then you complete. If you complete, then you get the smaller set. Okay, so complete algebra. Algebra gives rise to restrict to H1 of L coefficients in U lambda cross here putting U0. Okay, so instead of again doing something general, let me do something example. Example to have in mind is S3. Okay, because maybe one thing to explain here is what is the module structure that you restrict. So if you complete this, then you restrict your space, the space of modules that survive this completion is the things that you wanted. So how does an element of this space give rise to a module structure? Maybe that's one thing to explain. So this is, again, apologies, this is just some basic topology. So a rank 1 module is just the same thing as an augmentation. So we just need some kind of map from the homology of the base loop space down to lambda. Okay? And so what I'm going to do is I'm going to say, well, you can map this into the homology k plus 1 of the loop space cross S1 given by multiplying by the fundamental class of S1. Okay? And then you can evaluate this down to H k plus 1 of L, because if I have, if I have a base loop and a point in S1, then I get a point on L. Okay? And then if I have a class B in the cohomology of L, I can pair against B. And I get a number. So
there's no chain iterated integrals.
No.
It's like the math of the suspension.
Yeah, this is. Yeah, this is. I think, yeah. If you want something like that would be like trying to prove things like harm.
Don't you want? I mean, a linear map is not enough, right?
Yeah, you need to prove a compatibility with.
You need the map of algebra.
Yes, yes. I agree. So let's see what this gives you for S3. Maybe I should say this is the first order term, but I want to talk about S3.
Yeah.
Let's talk about S3.
First order term of what?
The first order term of the module structure.
Which is given by chain iterated.
I think of chain integrated integrals as giving me the isomorphism of harms of this module, but I think you probably, yeah, okay. Let me talk about S3. Okay, S3.
You're saying sorry, before you do that,
yes.
Paul, you're just saying if you want to prove that this is compatible with multiplications, you end up with a homotopy, that's the next term in chain iterated integrals or something like that.
Yes. And then if you wanted to make it co-chain,
yeah, well. Okay. So the whole thing is that when you actually want to talk about this as some kind of moduli space of rank 1 modules, I should have put A infinity modules here. And And on the homology, I should have talked about the A infinity structure on the homology. But okay. So for S3, so the homology of the base loop space of S3 is just an algebra generated by a single element u of degree 2.
But wait, sorry, why A infinity for the homology of the loops? What's A infinity?
So I think one answer is that if you didn't do A infinity, you would start getting the wrong. So I said things like this. So you want to think of this space as the space of rank 1 modules. Okay. Now let's take one of these rank 1 modules. Let's try to compute the self x of this rank 1 module. If we didn't do A infinity things, then we would get the wrong answer.
Right, but what type of A infinity on the loop space? This is my
Here?
right.
Oh, but this is just the fact that I mean, this is like a differential graded algebra if you use more loops.
But at the chain level, I agree. It's you need some infinity relations, but at the homology level, you talk about the homology of the loops with the Pontryagin product. Right?
Yes. That's perfect. It's perfectly associative, but the associative structure doesn't know everything that there is to know. So.
But it's also the associative structure is the first term of an A infinity structure.
Yeah.
And that's what A infinity. No, on the homology. And that's what was invented for A infinity.
Okay.
Can you story about S3? Are you going to appeal to the Greek structure on S3?
No. Yeah, I don't know what. So S3. So there is this element u in degree 2. So as a Z2 graded algebra, this is just a polynomial ring in one variable. And so what we want to see that picking B in H3 of S3 with lambda coefficients corresponds to the module, to the rank 1 module, which is lambda u modulo u equals b. Modulo the ideal given by this. So maybe we should call this like lambda sub b.
Sorry, I'm a bit lost. So you were talking about, you were describing YL some minutes ago, and so now you introduced loop space, and so what's your purpose here?
So the purpose is to explain that the origin of the algebraic structure on the origin of the analytic structure on the space of rank 1 and the space of Lagrangians. The space of unobstructed Lagrangians is supposed to have some kind of analytic structure. Where does it come from? It comes from thinking of it as a space of modules over this algebra. That's okay. So it corresponds to this module. And so how do we see this? Well, that's fairly easy because what does this generator U correspond to? So U corresponds to a family of maps. So in fact, it's some kind of maps from S2 to the loop space of S3. Okay, and so you can associate to this therefore a map from S2 times S1 to S3. Okay, and this map has degree 1. And if you take this degree 1 map and you see, well, okay, so degree 1 map. So if I pick, so given B in H3 of S3, if I apply this recipe, if I apply the recipe over there, I should get that U acting on, sorry. Oh yes, U. But anyway, so the action of U. So the action of U equals multiplication by B. This first term, and so I said, well, a rank 1 module is the same as a map from here to here. Paul corrected me saying, of course, it needs to be a map which preserves multiplication, but at least if you want to know, if you have this map, how do you want to think about it? You take kind of 1 in here, and its product with any given element should be its image under this map. That's what happens. So now I take 1 in here. I'd like to know what happens when I multiply by a given element here, when I multiply by u. And since this map has degree 1, I see that I get exactly multiplication by b. So that tells me that the pair S3 equipped with b times the fundamental class of S3, where again I tend to abuse notation and think of this as an element of H3, that this corresponds to the module gives the module that I wrote over there, lambda b. Okay?
I have a very stupid question.
Yes.
After you say the space of rank 1 modules on the loop space the same as H1 of this module,
Yeah.
have already a structure as an analytic space, doesn't it?
As a linear vector space.
Yeah.
Yes.
What do you want more than that?
Well, if you would like to understand how this behaves with, so yes, that's some kind of, yeah, if you'd like to understand how this behaves with respect to Floer homology with other objects, then you don't know what it means. So again, this is like saying, I have a module, but if you want to think of it as a vector space, yes, but if you want to think of it as a moduli space of objects of the Fukaya category, that's not helpful. If the moduli space of objects of the Fukaya category is an analytic space, then the question is, what is the set of functions on a given domain? You could write down some formula, but then you have to, if it's not natural, then you don't know what to do with it. Okay? Now the claim is that in this case, so the corollary.
Maybe that it's just a tangent space to the module?
No, the structure sheaf of this domain in the moduli space is actually represented by the base loop space of the Lagrangian.
That's a different structure sheet than what you would get on a vector space.
Well.
What's a vector space? Isn't that lambda star coefficient?
Yeah, okay. He said this is vector, but this is not too far from being vector space. Yeah. So again, you want to know where does the structure sheaf on this come from, and the claim is that the structure sheaf on Y of L is, comes from this object. Okay? So what do I mean comes from? It's actually a little bit delicate because this thing in general is non-commutative. Okay? But we have these two examples of Tn and in fact also odd spheres. So this is product of odd spheres. This is true on the nose. That is, they're just isomorphic. Okay? So now, why is this useful now? So before, what?
Is there some general rule that makes it commutative?
No, the base loop space is not in general commutative.
But in your case it is.
In your case it is, yeah.
Why is that?
Well, for
the torus is a group.
Exactly, odd spheres are, yeah. The torus is a group, and so is S3. And so is S3, and the other ones, they are rationally groups. So, okay, I lost my train of thought. Yes. So now, what that means is that before when I said, so before we interpreted M0 as some kind of assignment of an element of lambda, of a curvature to each b in the space Y of L. Maybe this is something to say. Before we talked about curvature, M0 being unobstructed. What does it mean? It means that you take a b and you get some number, and then you ask yourself, is this assignment continuous, or is this whatever? But with this object, so in terms of H of this homology, at least the part of the curvature becomes just an element of this ring. Of course, that's what we should expect. I mean, if I tell you that this is somehow, you should think of it as a space of functions on this space, and here we were talking about assigning to everything in this space a number, well, that should lift to saying that we have an actual element of this ring. Okay. What element of that ring is it? Well, now we get this so this is given by you take the base point, you take the moduli space of holomorphic disks passing through that base point, you take the sum over all of them, t to the energy of beta. Okay? So you take all moduli spaces of holomorphic disks in all homology classes, you evaluate them at the boundary, and you get some cycle, something in homology of the base Lipp space. And then you take that and you multiply that by the energy. And now you see why we had to complete. Okay? If you don't complete, this series doesn't make sense. So this only makes sense after completion. Sense after completion. Okay, so I have 2 minutes and I'm not going to say anything of substance. All I will say is the following thing. So what I've explained is basically everything that I have done so far. It really didn't require, except for this discussion of this P2, it really doesn't require much analytic geometry, because a lot of what we're doing is we're saying we have these domains, we have these analytic domains, we have these domains, and then we have these functions, and then we cut down the domains by the functions. So that's basically, we're just using the Zariski topology. Okay? But now, if you want to, somehow the usefulness of rigid analytic techniques is that actually there are other kinds. So this, there's a finer topology than this we could use, and that's the, well, I guess it's called, it's the topology that Tate introduced. Tate, G topology. And the difference between them is like this. The difference between them is that in Tate's G topology, if you take like an annulus of, by radius A and B, and you take another subannulus of say radius C and D, then this is actually an open subset of that. Okay, and the reason this is useful is that later, kind of in some other lecture series, if you want somehow to kind of patch things together, the natural way to do it in symplectic topology is to try to kind of build things over annuli like this and over annuli like this and glue them over intersections. Okay? And if this doesn't make sense in some kind of Zariski sense. This is not just cut out by setting some equation equal to 0. It's cut out by some constraints on the norm, on the valuation. And that the topology that is associated to that is the one that, again, it's not, this is the thing. So it's a Grothendieck topology, but it's good enough. Let me just pretend it's a topology. And that's what allows you to do kind of, patching arguments, where you go from local things to global things. We didn't get to see that in these two lectures. Okay, thank you.
So I'm going to try and ask the same question about the change versus
yes.
the change versus cohomology. So this thing you have circled